This video is an introduction to refrigeration. Here, I will be discussing the commonly used unit of refrigeration, how to measure the performance of a refrigerator in its comparison with heat engines and heat pumps. Also, classification of refrigeration techniques with a brief introduction to all these techniques will also be done. I will also be discussing the development of refrigeration over the years in brief. So, let's start with the definition of refrigeration. Refrigeration can be defined in a number of ways. Here are a few definitions. The key points in these definitions is that the body or the system should be maintained or should aim to achieve a temperature which is much below the ambient temperature. In order to achieve this, sometimes heat may have to be removed and transferred mechanically to a area where it is not objectionable. Commonly in refrigeration, heat moves from a body at a lower temperature to a body at a higher temperature, which may require some external work done on the system. With these definitions with us, can you identify which of these can be considered as a refrigeration process? Option B and option D are the correct options. In case of option B, the system is cooled to a temperature much below the ambient temperature using a block of ice. Also, in case D, by creating a vacuum over the water surface, evaporation occurs at a much lower temperature, and the water undergoing evaporation absorbs the latent heat of evaporation from the remaining water in the container. The remaining water is cooled down and subsequently reaches the saturation temperature at the given pressure. The other cases, that is A, C, E, and F, are not refrigeration processes. Case C is an example of evaporative cooling, but the final temperature is much closer to the ambient temperature. The other cases are examples of spontaneous cooling processes where heat flows from a body at a higher temperature to a lower temperature, which in these cases is the room temperature or ambient temperature. There are numerous applications of refrigeration. The major applications of refrigeration can be grouped into these four equally important areas. The primary cost involved with air conditioning is due to the refrigeration components employed in the system. There are also recreational applications of refrigeration like ice skating, ice hockey, etc. Refrigeration also has wide applications in medical field, treatment of metals, construction, and many other such special applications. Chemical and process industry also widely use refrigeration. Refrigeration has contributed significantly in increasing the shelf life of food and also food distribution to far-flung areas. The most commonly used unit of refrigeration since long has been ton of refrigeration, also called ton, denoted by TR. This is also sometimes referred to as refrigeration ton. This ton refrigeration does not convey the mass of the refrigerating plant, but is a measure of its refrigerating capacity. The roots for refrigeration are in the ice making industry, and the ice manufacturers wanted an easy way of understanding the size of a refrigeration system in terms of the production of ice. To be specific, 1 ton of refrigeration capacity can freeze 1 short ton, which is equivalent to 0.907 metric ton of water at 0 degrees Celsius or 32 degrees Fahrenheit in 24 hours to ice at 0 degrees Celsius or 32 degrees Fahrenheit. The latent heat of fusion of ice is equal to 144 BTU per pound, where BTU is British thermal units. Also, 1 US ton is equal to 2000 pound. So 1 ton of refrigeration is given by this expression. This is equal to 12,000 BTU per hour, which can again be simplified to 200 BTU per minute. Nowadays, the most commonly used unit in many countries is the SI unit. 1 ton refrigeration in SI unit can be calculated as 1 BTU is equal to 1.055 kilojoule. So 1 ton in SI units comes out to be 3.5167 kilowatt. In this section, let us discuss the differences between a heat engine, heat pump, and refrigerator. The primary function of a heat engine is to provide useful work by drawing heat from a high temperature source and rejecting the remaining heat to a low temperature sink. In heat pump and refrigerating machine, work input is provided to transfer heat from a low temperature body to a higher temperature body. Here we can see that the same setup can be used as a heat engine or a refrigerating plant or heat pump. So let us see what are the differences between these two. Now let us see the differences between these setups. It is important to note that the Kelvin-Planck statement pertains to the heat engine, whereas the Clausius statement of the second law pertains to a heat pump or a refrigerator. A heat engine provides a net output of work, whereas a heat pump or a refrigerator consumes work to operate. The performance of a heat engine is measured by its thermal efficiency, whereas in case of a refrigerator or a heat pump, performance is measured as energy ratio or coefficient of performance, which is the ratio of the desired effect and the work supplied. Say TA is the ambient temperature. The figure here illustrates the application of heat engine, heat pump, and refrigerating machine. As can be observed, the same machine can be used either for heating or cooling. When used for heating, it is called heat pump, and when used for cooling, it is called a refrigerating machine. The main difference between the two is their operating temperatures. The heat pump operates between the ambient temperature and a higher temperature, whereas the refrigerating machine operates between the ambient temperature and a lower temperature. The performance of a heat engine is measured by its thermal efficiency, which is the ratio of the work done by the engine divided by the heat drawn from the heat source. In case of a heat pump, the performance is measured by the ratio of the desired effect, that is, heat supplied to the heated space divided by the work input. Similarly, the COP of a refrigerator is measured by the ratio of the desired effect, that is, heat drawn from the cool space divided by the work done on the system. Now the COP of a heat pump can also be written in this form. Which is equal to 1 plus QL upon WH, which is same as the COP of a refrigerator. Hence, the COP of a heat pump is 1 greater than the COP of a refrigerator. The refrigerating techniques can be broadly classified as natural refrigeration and artificial refrigeration. Some prominent examples of natural refrigeration are refrigeration using natural ice making by nocturnal cooling, evaporative cooling, cooling by salt solutions. Similarly, the most popular artificial refrigeration technique is the vapor compression refrigeration system, also known as VCRS. Then we have the vapor absorption systems. Then we have some non-conventional systems like solar energy based refrigeration system. Also, we have the gas cycle refrigeration, which is used for aircraft refrigeration. We have steam jet refrigeration system, thermoelectric refrigeration systems, and vortex tube systems. Refrigeration using natural ice is the oldest method of refrigeration. The natural ice used for refrigeration was either transported from colder regions or harvested in winter and stored in ice houses for summer use. With the advent of artificial refrigeration, the ice trade gradually declined. As we move higher into the atmosphere, temperature variations are observed. The troposphere, which is closest to the Earth's surface, has almost a linear drop as we move higher up. Beyond the troposphere, we have the stratosphere, which has a sub-zero temperature range of around -60 to -40 degrees Celsius. Ice can be made during night by cooling of water by radiation to stratosphere, which is at a temperature of around -55 degrees Celsius. This method was perfected in India and was very popular. The figure here shows an illustration of Bengali ice making, as described by Sir Robert Barker in 1775. In this method, ice was made by keeping a thin layer of water in a shallow earthen tray and then exposing the tray to the night sky. The tray is insulated the tray was insulated at the bottom using some kind of insulation like hay. This method is suitable only on nights with clear sky and with mild or no breeze, as the principal mechanism of this process is radiation. Next is evaporative cooling. It is the process of reducing the temperature of a system by evaporating water or some other liquid. It is the working principle of desert coolers as shown in this figure. This also finds application in air conditioning, cooling towers, etc. Human beings dissipate their metabolic heat by evaporative cooling of sweat if the ambient temperature is more than skin temperature. Animals such as hippopotamus and buffalo coat themselves with mud for evaporative cooling, as shown in these figures. Evaporative cooling has been used in India for centuries to obtain cold water in summer by storing in earthen pots. This is the Nalanda University, which also used a draft of cold air from the river to cool its interiors. Certain substances, when added to water, dissolve in water and absorb its heat of solution from water. This reduces the temperature of the solution. Sodium chloride or common salt can yield temperature up to -20 degrees Celsius, and calcium chloride can reach a temperature of -50 degrees Celsius in properly insulated containers. This process has limited application as dissolved salt has to be recovered from its solution by heating. Here is a list of the advantages and disadvantages of natural refrigeration methods. The principal advantage is that natural refrigeration techniques are inexpensive. Also, they are generally environment friendly. However, these processes are uncertain. They depend on local conditions and cannot be carried out continuously. Say, for example, nocturnal cooling depends on the cloud cover. On a cloudy day, nocturnal cooling will not be very successful. Similarly, on a hot and in a hot and humid environment, evaporative cooling will not perform very well. The basis of modern refrigeration is the ability of liquids to absorb enormous quantities of heat as they boil and evaporate. The history of artificial refrigeration began in the year 1755 when Scottish professor William Cullen made the first refrigerating machine, which could produce a small quantity of ice in the lab. Professor William Cullen of the University of Edinburgh in 1755 placed some water in thermal contact with ether under a receiver of a vacuum pump. The evaporation rate of ether increased due to the vacuum pump, and water could be frozen. This process involves two thermodynamic concepts, the vapor pressure and the latent heat. Here are only some of the important events in the history of artificial refrigeration. The history of artificial refrigeration starts with William Cullen, as already discussed, by demonstrating the production of ice in his lab. Before the refrigerator, people used ice boxes and ice houses. These ice boxes were made of wood with suitable insulation as shown in the figure. Ice used to be kept at the top of the box, and low temperatures were produced in the box due to natural convection. A drip pan used to collect the water formed due to melting of ice. The box had to be replenished with fresh ice once all the ice melted. Freezers were developed, which held their temperature at -23 to -18 degrees Celsius, which is safe for food storage. The first affordable refrigerator was introduced in 1927. It was called Monitor Top due to its appearance. Here is a timeline of the history of domestic refrigerator. The domestic refrigerator using natural ice or ice box was invented in 1803, used for almost 150 years without much alteration. The domestic ice box used to be made of wood with suitable insulation. Ice used to be kept at the top of the box as already discussed, and low temperatures were produced in the box due to heat transfer by natural convection. A drip pan used to collect the water formed due to the melting of ice. Efforts starting from 1887 have been made to develop domestic refrigerators using mechanical systems. The initial domestic mechanical refrigerators were costly, not completely automatic, and were not very reliable. The development of mechanical household refrigerators on a large scale was made possible by the development of small compressors, automatic refrigerant controls, better shaft seals, development in electrical power systems, and induction motors. General Electric Company introduced the first domestic refrigerator in 1911, followed by Frigidaire, hopefully I'm pronouncing it correctly, in 1915. Kelvinator launched the domestic mechanical refrigerator in 1918 in USA. In Japan, the first mechanical domestic refrigerator was made in 1924. In 1925, the USA had about 25 million domestic refrigerators, of which only 75,000 were mechanical. General Electric Company introduced the first refrigerator with a hermetic compressor. Soon, the open type, mainly belt driven compressors were replaced by hermetic compressors. The initial domestic refrigerators used mainly sulfur dioxide as refrigerant. Some units used methyl chloride and methylene chloride. These refrigerants were replaced by Freon 12 in 1930s. The refrigerants have their own vast history and have not been covered in details in this video, and they may require their own separate video for discussion. The domestic refrigerator based on absorption principle as proposed by Platin and Munters was first made by Electrolux company in 1931 in Sweden. The first dual temperature freezer refrigerator was introduced in 1939. Today, a domestic refrigerator has become an essential kitchen appliance all over the world, except very few, almost all present day domestic refrigerators are mechanical refrigerators that use a hermetic compressor and an air cooled condenser. The modern refrigerators use either HFC 134A or isobutane as refrigerant. This figure shows the vapor compression refrigeration system, which is one of the most widely used systems. The basic system as shown in the figure consists of an evaporator, compressor, condenser, and an expansion valve. The refrigeration effect is obtained in the cold region as heat is extracted by vaporization of the refrigerant in the evaporator. This system will be discussed in greater details in future videos. The mechanical compressor in vapor compression refrigeration system is replaced by a group of components in the vapor absorption system in order to carry out the refrigeration using low-grade heat energy. In the vapor absorption system, we have an absorber where an absorbent absorbs the refrigerant vapors, which is pumped to a generator where heat energy is supplied to separate the absorbent and the refrigerant vapors. The absorbent is again supplied back to the absorber, and this cycle continues. The evaporating vapors create a higher pressure in the condenser side and enable condensation at a higher temperature. The basic system as shown in the figure consists of an evaporator, a condenser, an expansion valve, and assembly of components to replace the compressor, that is the generator, pump, heat exchanger, and absorber. There are a number of combinations of absorbent and refrigerant. Here are a few common pairs: sulfuric acid and water and ammonia, lithium bromide and water. The vapor absorption refrigeration system has a pump, but the pump power is almost negligible. Hence, the system runs virtually on low-grade energy used to separate the refrigerant from the absorbent. In 1922, Balzer von Platen and Karl Munters, two students at Royal Institute of Technology, Stockholm, invented a three-fluid system that did not require a pump. At this point, I'd ask you to open your mouth wide open, like, like in the figure, and place your palm in front of it. Now, blow air onto it. Now, purse your lips or make a pout and blow air onto the palm. What difference do you feel? In the first case, you may have felt a warmth on your palm. In the second case, you may have felt cold air hitting your palm. This is known as Bernoulli's cooling. The reason for this is, in the second case, the air which was built up in your mouth suddenly, after coming out of your lips, expands, thus cooling down. As you bring your palm closer to your pursed lips, you may start feeling a warmth. Similar thing can be observed with a balloon. The air coming out of the balloon feels colder. So, if air at high pressure expands and does work, its temperature will decrease. Dalton and Gay-Lussac studied this in 1807. Sadi Carnot mentioned this as a well-known phenomenon in 1824. However, John Gorey, a physician in Florida, developed one such machine in 1844 to produce ice for the relief of his patients suffering from fever. Alexander Kirk in 1862 made an air cycle cooling machine. The basic system, as shown in the figure, consists of a compressor, an expander, and a heat exchanger. These days, air cycle refrigeration is used only in aircrafts whose turbocompressor can handle large volumes of airflow rates. Here is steam jet refrigeration system. If water is sprayed If water is sprayed into a chamber where low pressure is maintained, a part of the water will evaporate. The enthalpy of evaporation will cool the remaining water to its saturation temperature at the pressure in the chamber. The low pressure, around 8 to 22 millibar, required to evaporate water as a refrigerant at 4 to 7 degrees Celsius for air conditioning, can be obtained with a steam ejector. In such a system, high pressure steam at around 10 bar is commonly used. The COP of this system is somewhat less than the absorption system, so its use is restricted to applications where large volumes of steam are available when required, such as large steam-driven ships, or where water is to be removed along with cooling, as in freeze drying or fruit juice concentration. This video, edited with permission from ITW Vortex, shows the working mechanisms of a vortex tube system, as explained by them. The link to the complete video is available in the description below. In this case, air is supplied from a compressor to the inlet of the vortex tube. The compressed air enters a stationary generator where a vortex is generated. This vortex is obstructed at one end by a semi-opened vent. This video clearly shows the working principle of a vortex tube system, which uses compressed air and supplies cold air at one end and some amount of hot air at the other end. In 1931, French engineer Georges Rank discovered a phenomenon called Rank effect or vortex effect. The tangential injection of air into a cylindrical tube induces, to quote his words, a gyratory expansion with simultaneous production of an escape of hot air and an escape of cold air. In 1945, Rudolf Hills, a German physicist, studied this effect and published a widely read scientific paper on this device. Thus, the vortex tube has also been known as the Rank-Hills tube. The efficiency of the system is quite low. It is simple with no moving parts and produces instant cooling, but it requires a continuous supply of compressed air. Applications include spot cooling of machine parts, machining, electronic cooling, and also in cooling jackets for miners and firemen. In 1821, German physicist T. J. Seebeck reported that when two junctions of dissimilar metals are kept at two different temperatures, an electromotive force is developed, resulting in flow of current. This is something which all of us must have read. The EMF produced is found to be proportional to the temperature difference. In 1834, a Frenchman, J. Peltier, observed the reverse effect, that is, cooling and heating of two junctions of dissimilar materials when direct current is passed through them, the heat transfer rate being proportional to the current. In 1857, William Thomson proved by thermodynamic analysis that Seebeck effect and Peltier effect are related, and he discovered another effect called Thomson effect. According to this, when current flows through a conductor of a thermocouple that has an initial temperature gradient in it, then heat transfer rate per unit length is proportional to the product of current and the temperature. For a long time, thermoelectric cooling remained a laboratory curiosity as the temperature difference that could be obtained using pure metals was too small to be of any practical use. Also, insulating materials give poor thermoelectric performance because of their small electrical conductivity, while metals are not good because of their large thermal conductivity. However, with the discovery of semiconductor materials in 1949-1950, the available temperature drop could be increased considerably, giving rise to commercialization of thermoelectric refrigeration system. These systems, due to their limited performance, are now used only in certain niche applications such as electronic cooling, mobile coolers, etc. Efforts have also been made to club thermoelectric refrigeration systems with photovoltaic cells with a view to develop solar thermoelectric refrigerators. Let us now compare artificial refrigeration with natural refrigeration. Artificial refrigeration methods are continuous, whereas natural refrigeration techniques are discontinuous. Artificial refrigeration techniques are more reliable compared to natural refrigeration, which are uncertain due to dependence on local conditions and environmental conditions. Artificial refrigeration can work under almost all conditions, but natural refrigeration depends on local conditions. Artificial refrigeration are generally more expensive compared to natural refrigeration techniques. Artificial refrigeration, mainly in cases where we use refrigerants, have proved to have detrimental effect on the environment. and continual efforts have been made to decrease the effect on the environment, whereas natural refrigeration techniques are generally environment friendly. Thank you for watching. Subscribe and press the bell icon if you haven't already to get all the updates. Also, like and share the video so that it reaches more people. Click on the thumbnails to watch more videos on the channel.